be invoked on each object. So let's say we have a domain for the folder of finance, and it says that for that folder, only the actions of read and write can be implemented, but it cannot be deleted. So we give a specific set of permission on a least to know or on a need to know basis. Another thing on protection domain that we can see in the slide is the ability to execute an operation on an object, and which is called an access right. An access right is basically what the user is allowed to do. So we give the user the operation, the permission to do a specific write on the file or the folder or the specific object. So let's say it's a printer, it can only print to the printer, but it cannot execute file on the printer objects. So if it's a printer object, it has a specific kinds of access rights, which is a print, maybe it's the delete print jobs, but not read, write, or execute. Also, as we can see in the slide, a domain is a collection of access rights, each of which is an ordered pair in accordance with object name and right set. So we have the object name, so let's say it's a folder called finance, and we have the rights set to that object name. So the folder finance has the rights of read and write, but not execute. So let's see an example. Here we have a domain, look at the arrow on the screen, domain 1, that has inside of it object 1 that has the read and the write permission. Now object 2 has the read permission. So and on the right we can see domain 2 and domain 3, with object 4 has both read permission both to domain 2 and both to domain 3. So they basically, domain 2 and domain 3 need to intersect with each other and give the user the cumulative permission to that object, whether it's coming from domain 2 or whether it's coming from domain 3. We also see here that object 2 has the write permission on domain 2 and the read permission on object 3. Let's speak about more about access control and protection. In specific, a domain can be realized in a variety of ways. One of the ways is that each user can be a domain, each process can be a domain, and each procedure can be a domain. So a domain is not necessarily a general domain. It's in accordance to a specific write or specific operation that the user needs to do. So a user itself can be a domain, or even a process can be a domain, and a procedure can also be a domain. A procedure, let's say, for example, a procedure of printing or procedure of erasing files or modifying the files. This can also be a domain. Another thing that we can see in the slide is the role-based protection uses domain hierarchy. A role is a set of users or groups. So let's say a role is administrator or a system administrator or power user. This role, this specific role, gives a specific permission to that role. So let's say an admin role gives a full access permission to that object that it accesses. So each role gets permission of roles below it. As we can see in the diagram below, the admin has the permission of power user and user. The power user has the permission of the user, but the user do not have the permission of the power user nor the admin user. Let's discuss access control matrix. In access control matrix, the rows of the access matrix represent domains, and the columns of the access matrix represents objects. Each entry in the matrix consists of access rights. So let's look at the diagrams and see that domain 1 and object 1 has read permission. However, domain 1 and object 2 has read plus write permission, and object 3 has no permission in domain 1. Again, object 1 has read permission in domain 2, however, it does not have any permission in domain 3. Object 2 has no permission in domain 2, however, object 3 has the execute permission in domain 2. So think of it, for example, as a folder and a user. So let's say the user is the domain and the object is a folder. So the user would have a read permission on the folder. So let's say user 1, which is domain 1, would have a read permission on object 1, but would not have any permission on object 3. So let's say object 3 is the finance folder. The user would not have any permission to the finance folder because it does not belong to the group of finance. But however, user 2, which belongs to the finance group, would have an execute permission on object 3. And user 3, which belongs to the IT department, would only have access to the folder of IT, which is the read permission, but would not have any permission to the finance folder or the help desk folder. Let's speak a little bit about the Windows XP access control. The Windows XP access control is comprises from role-based access control. What I mean by that we have specific groups of administrators, power users, and regular users. Just 3 simple groups, which is basically classified as roles. A user is a specific user that is only able to run programs or read files, and a power user is a user which has a little bit of power, still not an administrator, but is able to copy files or erase files or even remove programs from the computer, but however, he is not able to install programs in the Windows XP. Installing programs in Windows XP requires a specific administrative permission. So for each object, several operations are defined. As we can see in the slide, we have the read, modify, change owner, delete, etc. Access tokens define who wishes to access the object. So an access token for a folder would be the set of permissions to that specific folder. It would have the read permission for the finance group, it would have the write permission for the IT group, and it would have the execute permission or modify permission to the help desk group. A security descriptor is used to define access policies for the object. It is also known as a SID. A SID is basically the user ID or the user index number of the user in the system to provide the computer a way to distinguish between 2 users, not only by username but also by a security descriptor. Also, system reference monitors determine whether the access request defined by an access token is approved. So when a user MOTI that has the SID of 1, 2, 3, 4 tries to access the folder IT, the computer basically compares between the token and the SID to see that if in the token, if it allows the SID to get an access to that specific folder. As we can see here in the screenshot, we have user ID. Each user has a SID, as we said before. So for example, this user has this specific SID, and computers, groups, and domains also have SIDs. As we can see here, the group's guest or the group's administrator also has SIDs. Security tokens used by the reference monitor to identify the security context. So we can see here that the administrator group has the allow permission on full control, modify, read and execute, list of folder contests, but however, the group of guests would have a different set of permission that will only allow the read permission or maybe the write permission, but not a full control permission. So this is the role of security tokens. It is used by the reference monitor to identify the security context of that specific object. So what is a security descriptor? So as we said before, each object has a security descriptor defining which operations are allowed on the object. So let's say it's a folder. So a folder would say which group has which permission to access that specific folders. If it's a printer and it's a color printer that prints double-sided, I would only want the members of the IT department to be able to print this to this printer. So I would give only the print permission to the IT department. So the security descriptor would have a specific permission to the IT department, and someone else trying to print to that printer would get the message of access denied. Also, the security descriptor, as we can see in the slide, consists of a header, a SID of the object owner, and the SID of the primary group of the object, and also optional lists. Optional list, as we can see below, is access control list, is the list of users and groups that are allowed to access the object, and system access control list, which is related to logging in and to quota enforcement. So the system access control list is not really an access control list of a folder. It's more likely an access control list of a whole volume or a whole drive. So let's say I have the C drive and it has 20 gig of free space. I would want to create some kind of a quota enforcement system that won't allow users to upload files more than the amount given to them. So let's say I have 20 users on the system. I would give no more than 1 gigabyte of amount of data allowed to be uploaded to that operating system. And if a user tries to upload more than 1 gigabyte, I would have them denied of access and let the administrators group know what it's trying to do. Let's see an example of an access request. As we can see in the diagram, we have here a user Martin, which belongs to a group of students. User Martin gets an access token, and it tries to do the operation of write. Write is basically mean either modifying the file or trying to delete the file. Now, it reaches the computer that has a reference monitor running, and the reference monitor basically checks the owner seed, the group seed, and optional lists to see whether the students group or specific the user Martin has a permission to do the task he wants to do. In this case, the task he wishes to complete is the write permission task. So we see in the reference monitor in the security descriptor that member of students group has the write permission, but teacher has denied permission of read. So in this case, in this access request example, the user Martin would actually get a write operation access because he is allowed to do that action in the security descriptor. So let's speak a little bit about how to implement security by operating system. So operating systems should handle user code trying to read memory regions, such as password file sensitive data. The operating system should see and should verify that users are not accessing sensitive areas in the data in the hard drive, and they're not accessing sensitive files such as the password files and trying to read them or even modify them. If such thing happens, we need a special alert being sent to administrator that he should know that a regular user or even an administrator user is trying to access those sensitive files. So the operating system should handle those kind of attempts. As we can see in the slide, also a user code trying to write to memory, such as changing operating system code or crashing the system and changing permission, should also be referenced and have recorded. Think of a user that accesses the folder of Windows, and it has a lot of sensitive operating system files, and if he has permission to them and tries to delete them or tries to modify them, basically the operating system would not reboot afterwards. So I want to show now a quick demonstration of the Windows folder, which is containing all the sensitive files of the operating system. So I would open my computer. And I would go to the folder C Windows System 32. All of the folders here are basically very, very sensitive. So the Windows should have some kind of mechanism to find out that I'm not erasing the file. But specific in Windows XP, it has a mechanism to detect if a sensitive file was erased, and it knows to restore it from a folder called DLL cache. DLL cache is a folder which contains all the sensitive DLLs and sensitive information of the operating system, and it continuously monitors the operating system to see if the operating system files were changed. If the operating system files was changed, I would get an alert, and the Windows operating system would try to restore those files. So if a virus attacks my computer, the operating system would identify if it tries to access a system-sensitive files and try to change them, and would try to fight back and change the files back to their original description. Now let's go back to the slide. Okay. So user code calling system calls, such as opening files, creating network connection, etc. We need to verify that all activities done by the users, we would have records of being happening. So let's say I have a sensitive file that has the correct permission. Let's say it's the file that contains the salary data of all the company, and the permission is only read permission by the finance department. But a user who tries to access those files, even if he does not succeed, we need to have some kind of operation of log that he tried to access the files, and we need to take care of this matter. Another type of operating system that should handle user code by, if it tries in error or intentionally wasting system resources, memory, files, etc. Let's say he runs a program, and this program specifically was not written very smart or very wisely, and this program basically consumes all the memory. It's also called memory leak. I need to find out which program is doing that, and to warn the user that a specific program is basically consuming all the memory in the operating system. So let's see the operating system components in a simplified version. It's for Linux and Windows XP. We have system management programs such as My Computer, such as My Documents, such as the calculator, or all the programs that comes out of the box with the system, with the operating systems. We also have user programs. User program is program that the user installs on his computer for his personal use. Examples for that can be Office, can be online games, can be program spreadsheet, and etc. Below that layer, we can see the kernel layer, which the kernel is basically a proxy between the programs which runs in the user space and the hardware. The hardware is all the CPU, is the memory, is the printer, all the hardware that we described before. So we need to make sure that the user programs or even the system management programs do not have direct access to the hardware, because if they have an access, then they can basically destroy memory or destroy even hardware if it's not monitored correctly. So the role of the kernel here is basically to proxy the connection between the user programs and the hardware, and to make sure that it does not cause or create any damage which is irreparable. Okay, so let's see in the slide the operating system chain of trusts. So basically the hardware trusts the kernel, but the hardware does not trust the user programs. The kernel trusts the user programs. So to make a long story short, the hardware trusts the kernel, which trusts the user programs. So we have a mechanism that each party trusts each other, thus creating a chain of trust that can have a legitimate use of user programs and resources of the operating system. Let's see more about trusted operating system. Ordinary operating system security features access control to files and resources. So an operating system would suffice in an access control files and resources, that folders and files would have a specific access control. Let's say to the group of the IT, I would have a read control, read permission, and to the group of finance, I would have the read, write, and modify permission, but not the execute permission. Also, authentication and authorization of user, as we can see in the slides. So we need to make sure that a user accessing the operating system would be authenticated and authorized before he tries to access resources or objects on the operating system. We also need to guarantee a fair access to resources. When we say that, we basically mean that a user should work in accordance to his roles. So let's say a user is working in the IT department, he should have a specific permission to the IT folder, and he should not have a no access to the IT folder because he needs to work. We need not to disturb him. He needs to do whatever he needs to do, but he should not do whatever he is not supposed to do. Another ordinary operating system security feature is protection of the operating system data. We need to make sure that the user cannot destroy sensitive data of the operating system, even though he has permission to do that, even though that he's the administrator of the operating system. If he erases an important file, we need to have some kind of mechanism to prevent him of doing that, or at least if he does that, we need to have a mechanism that the operating system would be able to restore itself, which also happens in Windows XP. Also, we need to make sure that inter-processes communication and synchronization happens in accordance to the operating system policy. We need to make sure that a process of a Word would not be able or would be able to inter-process with another process if it needs to. Let's say I have a Word document, and in the Word document you have an option. I will show a quick demonstration now. You have the option to send the file in an email. So let me open up my Word document. So in this Word document I can write whatever I want to write, and in the end when I want to print it or whatever I want to do, I'm also able to send it to a mail recipient. Now when I type the mail recipient, what the computer will do from the process of the Word file, it will open up my Outlook, which the Outlook is a different process. So basically in the background it needs to make sure that the Word is able to access the Outlook but do not misuse the privileges in the Outlook. So this was an example. Let me go back to the slide. This was an example of inter-processes communication and synchronization between two processes. Another thing that ordinary operating system security feature is logging and auditing. I need to make sure, the operating system needs to make sure that whatever access I try to do on the computer, if I try to log onto the computer or if I try to access a file or a folder that I should not do, that it will be recorded somewhere. So thus, auditing should be turned on the operating system to make sure that alerts is being triggered when a user is trying to do something which is not supposed to do. And moreover, or even not as even more important, when he tries to do a thing that he's able to do. But if it's a critical thing, I also need to know that he tried and he succeeded in doing so. Okay, so trusted operating system security features should include mandatory and discretionary access controls to system data and to system resources. Basically, it's big words to describe that a user should have only permission of the object it needs to access, and not more and not less. He needs to read the document, but he should not modify the document, and he should not delete the document, and moreover, he should not execute the document because it might contain malicious code inside of it. Another thing is that user authentication and authorization should happen when a user tries to connect, log on, or access a specific object. It cannot be imaginable that a user would be able to access a computer without being authorized in advance, because if it's not happening, we won't be able to know who did the crime or who did the legitimate thing of happening, and we won't be able to do satisfactory access control system. Another type of trusted operating system security features object reuse protection. When we say object reuse protection, we basically mean that we don't want a specific object to be reused again and again. For example, I have a file and I know it needs to get printed only one time, so I would have a specific permission for it to be printed only one time as in accordance to the security policy, but not a second time. Trusted path is a way of a user get intersected with the group he belongs to. So if a user has the permission read and the group he belongs to has the permission write, so the user should have the permission read and write because specifically he has the read permission, and because he belongs to the group that has the write permission, he would have also the write permission. Also, if a group is nested in another group, the group should also have the permission of the nesting group which is relies in. Another type of trusted operating system security is the intrusion detection. An operating system needs a mechanism to detect any intrusion attempts or any intrusion, successful intrusion to the system. Intrusion is being defined by means that an illegitimate action or illegitimate user tried to log on or tried to use permission that is not given to. Another trusted operating system security feature is complete auditing and logging of resource and data usage. As we said before, it's very important that even the successful and the unsuccessful things the user tries to do and succeed or do not succeed get recorded. Those tries should get recorded, and the administrator should see the tries and errors that happened in the operating system. Let's speak more about trusted operating system. The NSA, which is the National Security Agency of the United States of America, basically rated operating system by their security level. It starts by the C2, which is controlled access protection. It basically means that it's a computer that has an access of username and password, but it can be connected to the internet. It does not have any password policy. The password can be 1, 2, 3, 4, and no account lockout policy, etc., etc. In the B1, B2, and B3 operating systems, you have labeled security protection and actually a structured protection to the operating system, which basically complies of specific permission to specific folders, specific ways to log on to the system with complex password that contains uppercase and lowercase and digits, with specific ways to log onto the system that uses smart card or tokens or biometrics controls. And we have the A1, which is the verified design. And the A1 operating system, first of all, it would not have any connection to the network. And lastly, it would have a very complex access control list, which is comprised of a need-to-know basis of specific permission and a two-way factor authentication to each resource. So let's say I want to access to a specific resource. After I log on to the operating system, I would have to type in my password again and also present a second type of authentication, a two-factor authentication, such as a one-time password or fingerprint or retina scanning system. Let's speak a little bit about the trusted kernel. We showed before the diagram of the operating system, and we saw in the diagram that there was a hardware, kernel, and user programs and system management programs. In the trusted kernel, we have two layers of the kernel. One of them is specifically talking to the hardware, and the other one is specifically talking to the programs. At both times, none of them is talking to each other, in meaning that the kernel cannot speak to the hardware and the security kernel cannot speak to the user programs. Thus, it creates it brings on another level of security while creating another chain of trust, which the hardware trusts the security kernel, but it does not trust the kernel, and the security kernel trusts the kernel, which trusts the user space of the programs and the system management programs. Another type of protection in the operating system is something called a virtual machine. A virtual machine is a thin system software layer. It's basically a software that is designed to run another operating system on my operating system. If you know, there's a program called VMware. VMware is basically a software that is designed for me to install. If I want to, let's say, in my Windows box, I want to install a Linux box, it creates a virtual machine environment that the software thinks it has a hardware, but actually it's also an emulated hardware, and it's actually a software. So I want to show you a quick demonstration now. I want to show you the VMware program, and in a very quick way how it works. So I will open up now my VMware program, and we'll see how we create a new virtual machine. this is the VMware program. Here we can create a new virtual machine. So I will open up this wizard. I get a wizard, I press next. It asks me which type of virtual machine configuration I want. For that example, I would choose typical. Now it tells me the operating system. Pay attention that I'm running now Windows XP, and he tells me that I'm able to run a different operating system on that box. So let me choose Linux and Red Hat Linux. I press next. He tells me now the location of the virtual machine file that will be loaded from. And he asked me which network connection I would want to use. In this example, I would use bridge networking. So what it does, it basically gives the guest operating system direct access to an external Ethernet network. The guest must have its own IP address on the external network. And let me finish. And the virtual machine is ready for installation. So basically what I can do now is use an ISO image to load an operating system. So I have an ISO image of Red Hat Linux, and I can use it to download from the virtual machine file. So look what happened when I press the play button here, which is the power on. Basically, a new computer comes back to life and starts up. So it loads the kernel, it loads the RAM disk, and a new virtual machine comes to life. Now, soon I will be able to see that it's starting the installation process, and it's starting to detect drivers, which is actually an emulated software drivers that the operating system thinks it sees as hardware, but actually it's a software. So that's an example of an operating system which can run on top of my machine and basically act as a virtual machine. I will go back now to the slides, and we'll continue with detailing what virtual machine really is. So we said it simulates the real hardware. It runs on top of the system kernel because it's not really hardware, so it runs as a user program. It has several virtual machines can run on the same machine. I can load several virtual machines. One has Windows 98, the other one has Red Hat Linux, the other one can run eSafe virtual appliance, and even Novell or Unix or Solaris, etc., etc., etc. And each VM, each virtual machine, may support a different kernel, because a kernel is basically a part of the specific operating system. So the Linux kernel is by far different than the Windows kernel. So let's look at the virtual machine where it resides in accordance to the operating system diagram. So as we saw before, we have the hardware. We have the kernel of the operating system. And between the kernel to the system management programs, we can run the virtual machine. And the virtual machine itself is basically, from the kernel point of view, is just another program which is running. But from the virtual machine point of view, it has a kernel on top of it which can run a specific operating system. Let's speak a little bit about programming language-based protection. Programming language-based protection basically allows specification of access policies. It provides additional software for enforcing protection of access control. One specific example of programming language-based protection is the Java programming language. In Java, it has its own virtual machine. When a user runs a Java application, the Java runs an application in its own virtual machine that thinks it has its own hardware resources, its own kernel resources, and they do that in order to create a mobile code that is cross-platform, that can work in all the operating systems, because it does not need a specific kernel, because it uses its own specific kernel. So the Java programming language protection is handled by the Java virtual machine, also called JVM. each module of code is assigned a protection domain when initially loaded into memory. The protection domain indicates which operation this code module can perform. So let's say I load a Java program that does a chat mechanism, that then I would tell him that it can access all the chat components, but it cannot access other components which is outside of its virtual machine. So when resource is accessed, and as we can see in the slide, the stack is inspected to verify the access rights. When I say stack, I mean the program code, and which is inspected to verify the access rights. Okay, so let's see the next slide. The next slide talks about Java programming language sandbox. The sandbox, basically, it runs the code in a limited environment. It verifies each system call, and it verifies memory references. Now, the pros of this Java sandbox is it allows us to do a fine-grained control, and also it allows us to get a support for pro platform. But the cons in this sandbox is the efficiency. It's the need to express security policies that might have security vulnerabilities. So in a sandbox, it tries to run the specific mobile code, and it can have security vulnerabilities. But however, even if it is vulnerable, it won't cause any damage to the box itself, to the hardware itself of the operating system, because it runs in its own virtual machine. Let's speak about virtual memory. Virtual memory is one of the mechanisms to enforce memory protection. A virtual memory is basically comprises of a file on your hard drive, and it emulates or simulates the physical memory in the operating system. Each process has a continuous allocation of logical memory in that page file, or it's called a virtual memory file. And in practice, many processes are running on the same machine and in the same physical memory. So the virtual memory is actually a security feature, because the operating system maps the logical memories to the machine's physical hardware memory. And this mapping is called virtual memory. So think that I have the program Word, and the Word is using parts of the physical memory, but I would also give it parts of the virtual memory, because that part would be a part that I would allow to share with a different application, such as Outlook. As the example we showed before, that when I launch a program, when I launch the Word file and tries to send it to an email using Outlook, basically it uses the virtual memory allocation and not the physical memory allocation, because if it would use the physical memory allocation, it would have problems with clashing between two memory spaces in the physical memory. In virtual memory, we prevent that using that method. So as we can see in the slide, each process is only able to access its own memory segments. So to summarize this lecture, we discussed an implementation mechanism used for protection of computer systems. We saw, for example, the Windows XP access control. We saw that it comprises of three kinds of roles, which one of them was user, the other one was the power user, and the administrator. We showed that the administrator has the permission of its two predecessors, the power user and the user. However, the power user did not have the administrator permission, but it had the user permission. So we see that it's like a three-way trust, that each member of this trust has the permission of the two others that is below it, but as the one in the middle does not have the permission of the one above it. So meaning the power user would not have the permission of the administrator, but would have the permission of the regular users. We also described various mechanisms for implementing secure operating systems. We showed what is trusted computing, that we need to trust the user with a password or with a token or with a specific smart card, and we need to use a specific strong password, and the user needs to get locked if he uses his authorization more than he needs to. For example, a user is trying to guess a password, and he fails to do so for 5 times, so his user gets locked. We also discussed what is the characteristics of secure operating systems, that we need a good way for auditing, we need a good way for quota management, we need a good way for strong password protection, we need a good way for access list of folders and files. We gave the example of the finance folder so that it has a read access by the finance department, and the specific user who belongs to the IT department would not have the ability to access these specific folders. We also discussed, as we see